Welcome back to our series on mathematical statistics. This is Lecture 6, Part 3. We are at Video 18, and we are finishing up our discussion of MLE and MME. We have finished talking about maximum likelihood and the invariance property, unbiased estimators. In this video, we're going to discuss the method of moments and several examples, and then we're going to briefly discuss the mean square error as a measure of how good a point estimate is. So let's get started. The method of moments. This is best explained by an example. This is a very easy concept, but I'm going to start with this example and then summarize it at the end. All right. So in this example, X is going to denote the fractional amount of impurities in a randomly selected batch of a certain substance. So it's certain chemical or what have you. Or it could be dirt or who knows, but some substance. For example, if x equals 0.02 or x equals 0.02 means that the selected batch has 2% impurities. Assume that the PDF of x is given by this equation, so it's theta x to the theta minus 1 when x is between 0 and 1. And it's 0 otherwise, and theta is greater than 0. I hope you know what distribution this is. Okay, so let's get started. Okay, so let's see. This is example 1 for the method of moments. All right, so the mean amount of impurities in one randomly selected batch is mu equals E of x. So we're always going to find E of x. And since this is continuous, we'll take an integral, and x goes from 0 to 1. So it has to be x f of x dx, which is equal to 0 to 1 x theta x to the theta minus 1 dx, which is equal to the integral from 0 to 1 theta x to the theta dx, which is equal to theta x to the theta plus 1 over theta plus 1, and this is from 0 to 1, x equals 0 to 1. So this is equal to theta over theta plus 1, because x is 1. If x is 0, then theta plus x raised to the 0 raised to the theta plus 1 is 0. And then if x is 1, then 1 raised to the theta plus 1 is still 1. So we have this minus 0. So we have theta over theta plus 1 is our mean. Now, suppose a random sample of impurities. Assume a random sample of n batches is selected, and the amount of impurities is measured. And these are the random variables are x1, x2 up to xn. Okay? The sample mean of impurities is x bar. Okay? So the method of moments says that we will, to estimate, jumping ahead of myself, to estimate theta says that we take x bar equals E of x. So this is the, okay, so what we do is we set x bar equal to theta, over theta plus 1, okay? Now we have to solve for x bar. We multiply both sides by theta plus 1, and we get x bar, theta plus 1, equals theta. And then we distribute, and we have x bar theta plus x bar equals theta. And we isolate theta, so we're saying x bar, okay, so we're going to do the other way. We're going to say, so we're going to take this over here, so we're going to have x bar equals theta minus theta x bar, and then we can factor out theta on that side, so we have x bar equals theta 1 minus x bar, which means that theta is equal to x bar over 1 minus x bar. And this is our MME estimator. So we're using a tilde. This is the method of moments estimator. Okay, so this is the first example. Okay, now let's say, for example, if a sample of n equals 10 batches gives x bar equals 0.03, then the MME of theta is given by theta tilde equals x bar over 1 minus x bar. So we plug in for x bar, so 0.03 over 1 minus 0.03, that gives us this value, which is approximately 0.031 to 3 decimal places. Okay. Now, let's talk about the general form of the method of moments. So basically a definition here. So let x1, x2 up to xn be IID with PDF, f of x, and theta. You can do this for PMF as well. Okay, it's just that you use the summation for the expectation instead of the integral. Okay, so it's easy to apply to a discrete function. So, and let's assume that theta is a vector. So this should be theta of n sub n is a vector of one or more parameters. So remember that a vector of one parameter is a point, and a vector of more parameters is a vector in a hyperplane. Okay, the rth moment is, okay, so the rth moment is E of xr, this should say moment, E of x to the r is x to the r f of x dx. Okay? So in general, the rth population moment is a function of the parameters of the parameter vector theta. In other words, we're going to say E of x to the r is g of r of theta, and r equals 1 to up to, let's see, we said n here. We shouldn't say n, we should say k. All right, so let me do this, and let me rewrite this as theta sub k. And r equals 1 to up to k. All right, so there's we don't want to use n because we've used n here. So for r equals 1 to up to k. All right. So we're going to say let the rth moment be denoted by m sub r, and this is a sample moment. The rth sample moment being denoted by m sub r equals the sum of xi raised to the r over n. And we know the value of m sub r. It can be calculated from n, x1, x2, up to xn, right? So the MME of theta is theta tilde. It's the solutions to the equations m sub r equals g sub r of theta, r equals 1 to k. Okay? And where g sub r of theta is the expected value of E of x to the r. So in other words, we say that the sum m sub r equals the sum of x sub I raised to the r over n is equal to e of x to the r. This is what we're doing for each r. Okay? So that's the method of moments. So again, the method of moments consists of equating the population and the sample moments to each other. If the PDF or PMF depends on two parameters, then we have two unknowns and a system of equations. In other words, m sub 1 equals e of x1, m sub 2 equals e of x2, and this is g1 of theta 1, theta 2, or g2 and g2 of theta 1, theta 2. The solution to this system of equations is theta tilde, and that's the vector theta tilde 1 and theta tilde 2, and this solution is the method of moments estimator, or MME. Okay, so let's do another example. So we want the MME for the parameters of a gamma distribution. So let x1 to xn be IID f of x alpha beta, and this is x to the alpha minus 1 e to the negative x over beta theta to the alpha gamma to the gamma of the alpha on the bottom, and x is greater than 0, and if x is not greater than 0, then the PDF is 0. We want to find the MME for alpha and beta. Okay. So we have two unknown parameters, and we need the first and second population moments. So first and second population moments. Okay. So remember that e of x for the gamma is equal to mu, which is alpha times beta. Okay, and we've got the variance sigma squared, which is equal to the variance of x, is equal to alpha beta squared. Right? And this is also equal to e of x squared minus e of x quantity squared. Very important to know that. This can be written as e of x squared minus mu squared. Now we need to solve for e of x squared. So e of x squared is equal to sigma squared, which is alpha beta squared, minus mu, which is alpha times beta quantity squared, and we have alpha beta squared minus alpha squared beta squared, and I can factor out a, okay, I don't need to. All right, we'll leave it there. Okay, so this is the second moment, and this is the first moment. And then we have the sample moments. So those are the population moments. The sample moments are m1 is equal to 1 over n sum of xi is equal to x bar. And m2 is equal to 1 over n sum of xi squared. Okay? So we need to equate these together. Equate the population and sample moments. So we're going to set m1 equal to ex and m2 equal to ex squared. So this gives us m1 is x bar is equal to alpha beta, and we have m2, which we solved was, let's see, this is going to be a plus here. Okay, so ex squared, this is plus. So we're adding mu to both sides. So I have to make sure I get my signs right up here. This is a plus, this is a plus. Okay, so m2 is alpha beta squared plus alpha squared beta squared, and that is going to equal 1 over n sum of xi squared. Okay, so we're going to solve for alpha and beta in these. So solve for alpha and beta. So first, we'll say that alpha tilde, whoops, not a good tilde, let's write that a little bit better, is equal to, and so we're looking at this equation here, and we're going to solve for alpha, so it's going to be x bar over beta. And this is my first one, equation. And then 2, so 2, I need to solve for beta using the second one. Okay. And so the second one, I have this equation. So I'm going to say that I have beta squared. I can factor that out of both of these. So I have beta squared, alpha plus alpha squared equals 1 over n sum of xi squared. Okay. Now, so now I'm going to substitute in for, so really I should reverse this. This is something you find out after you've solved it, that you realize, hey, I needed to put this one first. Sum of xi squared is equal to, and we'll have beta squared alpha plus alpha squared. And now we're going to substitute in equation 1 here for alpha and make it alpha tilde. And so this is equal to beta squared. We've got x bar over beta plus x bar squared over beta squared. Okay? And so now we multiply through the beta squared, and we end up with beta x bar plus x bar squared is equal to m2. So now we can solve for beta. We only have one beta in here, so we can isolate it. So this implies that beta x bar is equal to 1 over n sum of xi squared minus x bar squared. And this implies that beta is equal to sum of xi squared minus x bar squared over n x bar. And so let's see, how did I mess? Okay, so this is only for that. So I messed this up. Let's rewrite this, because the n is only with this term. So we're going to have to keep it with this term. So we have beta is equal to 1 over n sum of xi squared quantity minus x bar squared all over x bar. And this is my beta tilde. And so here now in the first equation, I'm going to change beta to beta tilde. Okay? So I don't want to have to substitute in for beta tilde because it's really complex. But so it's really, it has to be the tilde down here, or you're not really specifying the MME here. Okay? So that is the solution to this problem. Now let's look at example 3. We're going to let x1 to xn be IID normal with mu, mean mu, variance sigma squared. Find the MME for mu and sigma squared. Okay. So with this, we simply set, we know that E of x is equal to mu, and so, and we know that, that's not implying anything. We know that M1 is equal to x bar, okay? And so we set these equal, so therefore mu tilde is equal to x bar, okay, for this. That's easy. And then we have that sigma squared is E of x squared minus mu squared, which we're solving for E of x squared. Oh no. E of x squared is equal to sigma squared plus mu squared. And So now we know that M2 is equal to 1 over n sum of xi squared. And so we're going to say this implies, so this is 1, so for 2, this implies 1 over n sum of xi squared is equal to sigma squared plus mu tilde squared, okay, which is equal to sigma squared plus x bar squared, okay, and now we only have sigma by itself, okay, or sigma squared by itself. So we have that in only one term, so we just solve for sigma squared. Sigma squared equal to 1 over n sum of xi squared minus x bar squared, and this is our MME. So I can rewrite this as sum of xi squared minus nx bar squared over n if I like. Okay, so either one of these is okay. Okay, so that's it for that. Now, the last thing I want to talk about very briefly is the mean square error. So the mean square error, this is the most common measure of how good an estimator is. Okay? So some people, so smaller is better because this is error. You want the least error as possible. So the MSE, this is a formula you need to know. So we square the bias and add the variance. So if it's unbiased, this term would go to 0. And we'd just be left with the variance of the estimator. Okay. Now, you might automatically think that unbiased estimators are the best, but here I'm telling you that's not always true. Not always the smallest MSE available. In other words, S squared, it's biased, but it's still one of the best estimators. It has one of the lowest MSE of all the estimators. We can find unbiased estimators. They're really not great to work with. They're pretty complex and hard to use. And if you think about S squared, how complex it is already, imagine something worse. So we use the MSE to determine how good the estimator is. Don't just assume because it's unbiased that it's a better estimator than a biased estimator. You need to calculate the MSE to do that. Okay, so that's it for this section. I hope that has helped you understand maximum likelihood estimators and method of moment estimators. Method of moment estimators may seem easier. It depends on if you already know the mean and the variance or not. Okay, so that's all for this video. If it's applicable, make sure that you update your formula sheet or your list of definitions, your list of distributions. But as always, if you have questions, please come to virtual office hours. I'm happy to help you. If you can't wait, if you need help before then by all means email me and I will get back to you as soon as possible. Until then, please take care of yourself and we'll see you next time.